And if you have been enjoying these episodes, then please consider liking and subscribing. And in the meantime, let's get started. Lately, the problems have been getting easier and easier. I don't know whether it is by design, but it just seems to be easier than usual, the earlier problem. So anyway, let's start with the next problem. As you can see, we've solved 45 problems and we are going to solve the next problem. This is problem 46. Let's create a new Jupyter notebook. We will call it problem 46 like that. And we are going to, like we always do, we are going to copy the problem first like that. It's called Goldbach's other conjecture. So Goldbach is a mathematician. I know of Goldbach's one conjecture. I did not know Goldbach has so many different conjectures, but nevertheless, it is what it is. So let's read the problem. Okay. Oh wow. So there okay. There seems to be squares somewhere over here. And we also need squares. So these are squares. So it's 1 square, 2 square, and so on. And we'll just keep it at that. Okay. So now let's read the problem. It was proposed by Goldbach that every odd composite number can be written as a sum of a prime and twice a square. Okay. All right. That's my cat. Okay. So 9 is this square and so on. Okay. It turns out that the conjecture was false. All right. What's the smallest odd composite number that cannot be written as a sum? Okay. I don't really see any. At least nothing immediately pops to mind. And no elegant solution pops to mind. So let's try to solve it the usual way, by brute force. So anytime we have primes, let's pre-compute a list of primes. Let's see whether we remember the sieve algorithm. So the sieve algorithm goes as we have primes as an empty array, and let's import some stuff. Okay, so now primes is an empty array, and we want to initially create a list of numbers that goes from 2 to n. So numbers is np dot it goes from 2 all the way to n. That's what we are going to call. I have somehow this is going to be a problem. Okay, I have to figure out how to change. I have converted it into right. Okay, so it's only within here that this is a problem. To n. Okay, 2 to n, like that. Okay. Okay, and now what we want to do is to, while the length of nums is greater than 0, okay, we want to first is nums 0, so we take the first element, or let's call it n0, and we will append it to primes because the first element is going to be a prime. So primes dot append n0, and we have to modify nums so that all divisors of n0 get eliminated. So the way we do that is nums equals nums, and we have to create a mask, and the mask is going to be nums n0 is not equal to 0. So if we do that, we should have a list of primes, and these two look like primes. So let us do that, and this I'm going to delete it. There's some problem with that particular. So let's create a list of 1,000, 10,000. Let's create 100,000 primes. 100,000 primes doesn't take a lot of time to do. Okay, so now that we have 100,000 primes, we are going to solve the problem. We have to smallest odd composite prime. So smallest odd composite number. Okay, so we are going to take numbers for I in range 100,000, maybe n equals 100,000. It doesn't matter, and we take a large number. Okay, so for that we want to take primes. So odd is 2 into I plus 1. So this is going to start with, if I0 is going to start with 1, we want to start from 1. So then if I is 1, then it's going to start with 3, and if odd in primes, just continue. Okay, so now we have odd over here as an odd composite number. So let's check all the way to maybe 100. Okay, if we print odd over here, these are all odd numbers, and yeah, they're all composite, so that's good. So we have odd composite numbers, and we want to see whether these composite numbers can be broken down into a prime and okay, now we need to get a list of prime numbers that are smaller than this number, so smaller than this odd number, and it looks like most of the numbers are pretty close to that, so we will reverse that. So this is what I mean. We are going to select all the prime numbers less than that. So the primes, we are so now you have a list of primes, but they are numpy arrays like that. So that this happens to be a numpy array of primes, and it goes all the way up to 1,000,000. So now we need primes that print odd. We need primes that go all the way up to that odd prime number. So let's do that. Primes, selected primes is equal to primes and less than that odd number. Okay, and I will say reversed. Okay, so we will look at the largest prime first, because it looks like these numbers are pretty close to these numbers. These primes are pretty close to the numbers that we are trying to get to. So that's basically what we're doing. And let's print this. Let's print and it's just like that. So let's see, 7, 5, blah blah blah, 15 is that. Why is it starting from? It's starting from a 9. Nine, 15. Oh, all the way up to 7 is it? Yeah, okay. So all the way up to 7 happens to be a prime number. Okay. So that would be why. Now we want to see whether a particular condition is true. Whether this particular condition, for example, for 9, this particular condition is true, and we have to check it for every single prime over here. So let's create a function that will check for that condition. Check for the condition, and it is going to return a boolean, so whether it's true or false, and the general thing is false. If we see the condition that it is able to achieve, then it will return a true, otherwise it's going to return a false. And the number is n, which is an int, and we are looking at the odd number, and we want to take this and put it inside here, right? Because we don't want to worry about this outside. And given the selected primes for s in primes, okay, we want to subtract this from the number and divide by 2 and see whether it's square. So we want to take the number that's odd minus the prime, which is the one of the selected primes, s, or we can call it p for prime, p. and we have this. Now we divide by 2, so by 2, and we take the value, and that represents the number square. So if okay, square root of v, I should probably take the square root of this entire thing, and if this is an integer, is the same as v, I should return a true, else I should return a false. And over here it will be oddly satisfying if I print odd, and odd equals, let's just print the equation over here. Okay, odd equals the prime p plus 2 times I 2 times v square. So that's the equation, and I'm going to return a true over here. And I need to, at this point, check if check condition. Oh, I haven't actually executed that condition. Odd, then break. I go from 1 to 100 and see whether we have something. If not, so let's see. 9 is that, 15 is 13 and 1 square. Wait, and this is also okay. Okay, 21 is 19 and 2, and 25 is 23 . Twenty-seven is 19 and 2 square. Okay, so 33 is 31 and 1 square. Okay, so most of these are passing, so we don't want to print this. Okay, and we want to yes, what happened? Okay, all right. There's nothing all the way to 100. That's 100,000. Okay, so some number over here seems to be the result. I don't know if this is the answer, but let's check. Yeah, these problems are starting to get easier and easier every day. So I mean, let's stop over here. We'll continue next time. But again, if you like seeing all these problems, then I would highly encourage you to like and subscribe. It will keep me motivated to solve more problems. And I will see you next time. Take care.